One of the best ways to get more mileage out of your 6800 computer is to install and run the Flex operating system. Flex was essentially the CP/M of the 6800 world. However, if your 6800 machine happens to be the Altair 680 like you see here, that's not going to be too easy to do, and that's because there was never a floppy disk controller or floppy disk system made for this Altair 680 computer. But today I'm going to demonstrate a way to run Flex on this computer without having a floppy controller and without having floppy disk drives. To do it, we're going to use a serial interface board to transfer the disk data to and from a disk server that runs on a PC, or maybe on a Raspberry Pi for that matter. Here's the serial interface board we're going to use. This is the 68 UIO. This was made by MITS for the Altair 680. It has two parallel ports on it. That's these big 6820s, and it has a single 6850. That gives us a serial port. The actual connection for the serial port's over here on the left, and we'll see that later when we get this all hooked up. And then for the disk server, that part's really easy. That software already exists. I created the first version of that about 10 years ago to go and support a floppy disk controller I made for the 8080, the Altair 8800 computer. And that same disk server can serve up disks for Flex just as well as it can for the Altair and other systems. So that part's done already. Back to this board, what we'd like to do is run this at the fastest possible baud rate so that the performance of the system feels similar to using a floppy disk drive. Now up here in the upper right corner is the baud rate generator. This dip switch right here goes straight into the baud rate generator chip and allows you to choose from a number of standard baud rates all the way up through 9600 baud. Now this would work at 9600 baud, but it would feel very sluggish. We'd really like to run much faster than that. And fortunately, this baud rate generator makes that pretty simple. One of these switch positions, actually here when they're all zeros, instead of using one of the internal baud rates, selects a baud rate that comes in on pin 15 externally. They call that the MUX input. So all we have to do is put a higher baud rate clock that we want in on that pin 15, and we can select that by having these dip switches set to 0 like you see here. So where do we get that higher baud rate clock from? Well, fortunately, this baud rate generator makes that simple as well. This is a standard baud rate generator crystal, and this chip exposes the first 3 divide by 2 stages coming out of that crystal on pins 1, 2, and 3. So you get the crystal frequency divided by 2, divided by 4, and divided by 8 on pins 1, 2, and 3. And those frequencies happen to be 76.8, 38.4, and 19.2 kilobaud. Now I'd like to run this at 76.8, that would be really fast. However, the 6850 UART that's standard on this board, its maximum clock rate is going to be the 38400 in terms of a standard baud rate. Now we could install a 68B50 instead of the original 6850, and it could handle the 76.8. However, then we run into a limitation of the Altair 680 computer itself, and that is because MITS hobbled it to run at half of its normal speed. It runs at just 500 kilohertz instead of 1 megahertz. The receive loop can't keep up with 76.8 on this machine. So we're going to be having to run this at 38.4 instead. All right, so all we have to do is pick up pin number 2, which has a 38.4 baud clock on it, and jump it over to the MUX input. Let me just show you that mod here on the back real quick, show you how simple it is. Now it's not that blue wire you see, it's that little jumper wire right there, going from pin 2 to pin 15, and that's it. That's the only mod required, and then at that point, this board is ready to run at 38.4 for us. Very simple. Now the only other hardware requirement we have to worry about is RAM. Typically, Flex ran with 48K of RAM. Flex itself, the memory image of the memory resonant part of Flex, was up at A1000 through C1000 in the top of that 48K. However, we can't get 48K of RAM in this system using original RAM boards and the UIO board we need. That's because it would take 3 of the 16K boards, and there's only room for a total of 3 boards inside this computer, if you recall that from some of the earlier videos about this computer. So to get our 48K, I'm going to use this, this modern RAM board that another hobbyist has made. It allows us to fill all the way up to the bottom of the EEPROMs if we needed to. If you want to learn more about this board, it's great to have for your Altair 680. I put a link to it in the description of this field if you want to get one. All right, so with the UIO ready to go at 38.4 and our RAM board giving us 48K that Flex needs, hardware is ready. The disk server already exists and it's ready. All we have to do now is create a version of Flex that can run on this Altair 680, and instead of a floppy disk controller, use the serial interface board to do its communication with the disk driver. Sounds complicated, but in reality, Flex was fairly easy to port. And we'll go over to a computer and take a look at how that's done now. Now, typically when I've done development like this in my other videos, you've seen me work on vintage machines and use vintage tools to do the work. But since this particular project is going to have to use a PC as a disk server, it's definitely nothing somebody back in the day could have done. So I'm going to go ahead and use a PC to do some of my development. The final parts of the development will have to be on the vintage computer to finish it all up. Now, the memory resident portion of Flex is built from 3 files that you see here. The primary file is this Flex 3 core file. This is all the parts of Flex that are the same no matter what hardware it runs on. It doesn't change, so it's just a binary file provided on the Flex disk. I've got it exported here to a PC in an S-record format so I can easily load it into the Altair 680 to get us started. The other 2 files are a console driver file and a disk driver file to handle the particular hardware characteristics of the computer you're porting it to. Now, they give you examples for these 2 files. You're not starting from scratch, so it's not that hard to write these. There's basically a jump table here at the start of the file. If you look, here's a routine to check for the input status from the console. Here's a routine to output a character to the console, input a character from the console and echo it. Up here at the top is input a character and don't echo it. Look right here, here's an entry point to jump to the monitor. That's if you type the mon command, it just now knows where to jump to the monitor. This, of course, will take us to the Altair 680 monitor. These other inputs, these other entry points are for handling a timer interrupt. Timer interrupt is used by Flex to take care of a background spooling capability. I have no I have no timer interrupts available on the 680, so all those entry points basically do nothing. The rest of this is pretty much the same code that it came with. All I had to really do was change the address of the 6850. That's these 2. The sample code actually used a 6850 as the console interface. So very simple input-output kind of routines. All right, this file also includes the end of memory address, and we have it right below 8000. We're using all the memory right up to the start of Flex. And then it also includes here in the syntax used by the assembler in Flex, this tells it the entry address of this program. And when we build the system file and put it on disk, this will become the address that the bootloader knows how to jump to the entry address of Flex. All right, the disk driver also has a jump table here in the beginning. You read a sector, write a sector, verify a sector, restore to track 0, select a drive, see if the drive is ready. There's a quick check for that, cold and warm start, and then seek to track. Some of these aren't really needed. I'm not going to bother with a verify routine because it's, of course, all done by the PC anyway. The seek to track isn't really used by anything, so I didn't bother implementing that. But the rest of this then just does read sector, write sector, just like you would have through a disk controller, except I'm sending that data through the serial interface server. And you can see down here I have routines to send out to the disk server, and I have routines to receive from the disk server. And that's it. Now, they only give you 256 bytes to squeeze all this in, so it has to be a fairly short server, fairly short disk driver. Although, if you have extra RAM like we do, we could expand and go higher. But I try to fit it into the original 256 bytes just to be consistent with a typical early development. All right, so now the next step we need to do is get all these in a format where we can load them into the Altair 680 to get us started. The Altair 680 can handle S-record files. That's how it loaded programs from paper tape. So we've already got the core file in S-record format. I just need to assemble these 2 into S-record format. And I have a cross assembler on here that I use all the time, so we can do that. Let's go ahead and assemble the console driver, and we'll assemble the disk driver. And at this point, I've got my listing file and my S-record file for all 3 of these. So if I upload this Flex 3 core file plus the console driver plus the disk driver. At that point, I have a full flex memory image in memory on the 680. And I can just manually jump to it using the monitor to that AD00 address we saw. That should start up Flex. All the boot process does, if you were to load it from disk, is load this same memory image into memory ready to run and jump to it. So we're just going to do that manually to get us started and then see what we have to do after that to finish up the process. I've got this 680 ready to run. Try loading Flex for the first time. Back here on the left, this is a connection for the serial port from this board. That's going to go to this DB25. That's going to hook to the PC disk server. This other DB25 hooks down to the main board, and that's the console connection on this Altair 680. Now back in the day, the console on this would have typically been a teletype. Of course, that serves as an operator console, but also as our mass storage for this. You could read programs in using paper tape, and those programs would be stored in S-record format. And in the monitor was an L command for load that would load S-record files through the console port into the computer. And that's how we're going to get Flex loaded for the first time. We'll hook this to a terminal emulator on our computer, which will act as our operator's console. And if we just send a file through that same port, an S-record file, then the load command will work and we can load those Flex files that we just created. All right, so let's get this going. We'll power it on. Go halt, reset, run. And now the monitor's up on the computer, and let's go over and start using it from there. All right, so this will be our console for using the 680. Now we're in the monitor of the 680. We can examine a memory location, look through a few of those. We can change them to different values if we needed. But also in this monitor is the load command for loading S records from the paper tape that is our teletype. Well, in this case, we can just send those directly as a file from here, and it's the same as if it came in from the teletype. So first, I'm going to load the Flex core file. This is all the parts of Flex that don't change no matter what machine it's on. And of course, this is by far the largest part of all this. And at that point, then we'll be ready to load the console driver. Let's do a load for that. That's con drive S19. That's very short. And then finally the disk driver. It's not much bigger. All right, and at this point, we have the entire Flex memory image, including our console driver and disk driver for this serial 680 solution, all in memory, ready to go. Entry address for that is AD00, as we saw in that con driver file, and we have Flex up and running. So let's put in today's date, and now we're sitting at the disk prompt, the prompt for Flex. Now, if you've watched me port Flex in other videos, you realize at this point I am excited, but then at the same time, I point out that we have a whole bunch of work to do because there's not a thing we can do with this until we get a disk built up that has all of Flex's commands on it. And that's because there's almost no intrinsic commands in Flex. The only one you probably would use is the monitor command, which we saw in the con drive file, just jumps back into the monitor that you specified. In this case, of course, we have it go to the 680 monitor. AD03 is the warm start entry point for Flex. So now I'm back into Flex. There's a big chicken and egg problem of getting your disk formatted, adding the structures that Flex needs, and then getting all those commands on a disk when you don't have any of Flex's commands to do it with. And that was a problem to overcome, and I've shown a couple of different ways to do that in those previous videos. But it's actually not a problem at all for this particular configuration, and that's because there's a good collection of disk images already available. For example, let's take a look at the serial disk server. I've loaded this 6800 flex.disk as my boot disk. This is just a copy of a distribution disk, single-sided, single-density format, probably archived 10 or 20 years ago or more. And so I actually do have a disk in here ready to go. Now it doesn't boot the right operating system, but that doesn't matter because I booted here manually by loading it. So I can do a catalog and see what's on the disk. And if we do a catalog of all the .cmds, you can see the various commands that are part of Flex. Here's the catalog that we just did to look at files. Here's list to look at files. Here's copy to copy files, rename, delete. Here's the editor, assembler, etc. Also on this disk is the actual memory image of Flex ready to boot this disk. Well, this disk was made for a Southwest Technical 6800 computer. So this flex2.sys is everything that we just loaded manually except the console driver and the disk driver are for a Southwest Technical 6800. So obviously we can't boot this disk, but we can certainly use it as a data disk, which we are, and we have all our commands on it. Now I would like to create my own disk, and so on the second drive I've created a disk, and I'm calling it Serial Flex. And on this, I'm putting the things I like to have on my Flex disks. And I can see that by doing a catalog of drive 1. What we're going to do is work with this disk from here on out. So I'm going to assign the system disk and the work disk to be this. This is kind of like doing a B colon in in CP/M. And I have a few more commands on here I like. Here's a wide format catalog command. There's also dir like in CP/M here where it lines up the extensions in columns. There's a cat full where you get full information about all the files. Also on this disk is I have a couple of utilities that I put on pretty much any computer I create. Whoops, not asterisk. Okay, well that worked good enough. PCGet and PCPut. These are X modem transfer commands that allow me to get files in from a PC and write them back out to a PC into this file system. I just took the ones I made for the Altair, for the Southwest 6800. All I had to do is change the address of the UART, and now they'll work here on this machine. So this will allow me to get files off of the PC that we need, because the rest of this development we're going to actually have to do here on this machine. What we want to do is combine the Flex core file, the console driver that we wrote, the disk driver that we wrote all into one .sys file like we saw on the drive 0. So to illustrate that process, let's do the console driver first. It's smaller. I'll do a PCGet for the console driver source file. I'm going to call it a .txt, even though the original is actually a ASM. Doesn't really matter. Let's see, console drive.asm. TXT is the assumed extension by the assembler, the editor, list, etc. It just makes it easier. I don't have to type it. But if I did ASM, I could always just manually type that. All right, so this will assemble the console driver. It will create a binary file in the format that Flex uses. And then the listing just comes to the screen. That way it doesn't have to use up all the disk space that a listing takes. You can force it to write a file, but by default it just comes to the screen. All right, so here's the console driver going by. And now we have a .bin file for that. And then we'll do the same procedure for the disk driver. I've already done that ahead of time just to save a bit of time. So if you look here, we have the console driver and the disk driver bins. And what we want to do is combine all these into a single .sys file that will be the boot image that the disk loader will load to start up Flex. So that command to combine binary files is append. So we'll append the flex.core file, the disk drive binary file, the console drive binary file, and let's see, we'll call it serialflex.sys. Now what's interesting is this isn't really just appending them to each other, it's really combining them. And that's because the binary format in Flex was essentially a binary S record format. You did not have to have just a contiguous block of binary data like you did in CP/M. And I'll show you here in a minute with a map command. So if we do a map on serialflex.sys, what this is going to show you is the various data records that are part of this and how kind of space they spanned. So there's a chunk of data from AC100 to AC3A. Here's a chunk of data that's only 1 byte long. Here's another small chunk of data, just 4E to B2. Our disk driver, where's that? Here's our disk driver, BE80 to BEFC. And you can see these aren't necessarily even in order. We're going up, jump to B, back to AA. So the binary formats don't have to be contiguous and they don't even have to be in order. And so when we did this append, it actually merged these together as needed to make this final output file. And the very last thing in there is the jump record to where to enter. So this file is enough to load it and tell it where to jump. So at this point, we've got the bootable image of Flex right here, serialflex.sys, ready to go. So now the next question is, well, how do we make this disk bootable? Well, you realize, well, I've got a few steps ahead of me. Number one, I need to write a disk bootloader that goes down on sector 0 of this drive that a ROM bootloader loads. So the typical boot procedure would be you jump to a ROM, it loads sector 0 off a disk into RAM and jumps to it. What you load it off a disk, then loads Flex. And that has to know where this serialflex.sys file is and know how to load this oddball binary format of Flex. So we've got some work to do. We need to write that Flex loader and we need to write a ROM bootloader. So let's go ahead and do that step next. So in order to boot Flex, we need to load that system file we saw. We called ours serialflex.sys. into memory as part of the boot process. We need to write a loader that is stuck onto the first track of the disk down on track 0. I've called it flexload.asm. This is a program just like the console driver and the disk driver where they give you a sample to follow, so you're not starting from scratch. So here's the version I'm making for loading Flex with our serial port instead of a floppy disk controller. This loads at A100. This is the address that most all those commands you saw in Flex execute at. This is a hole right up in the middle of Flex. It's about 1.5K, where any of the programs that are smaller than that can run. And then that way, those commands don't affect, for example, BASIC or the assembler or the editor or some other program down in low memory. You can actually run commands without affecting any of those loads and jump right back into them. But that's kind of a separate topic. So anyway, this loader is going to get pulled in off a disk and run at A100. Now at offset 5 and 6 is very important in this file. It has to be a spot to put the track and the sector of the very first sector of the system file you want to load. Now, of course, you're not going to know what that is, so it's just got zeros in here for now. But after this is put onto track 0, then you run a little program called link, where you give it the name of the file that you want to boot. So, for example, if it was called flex.sys, you would say link flex.sys. Our case, it's searflex.sys. So we'd say link searflex.sys. Link goes to the directory, finds out the track and sector where that file starts, and pokes it into the first sector on track 0 at offset 5 and 6, so that now this program knows the starting address of the system file to load. Note that you can have 3 or 4 system files on that disk, and whichever one you want to use, link that, and then when you reboot, that will be the system file that runs. Now, once it's got that first sector, the rest of the file is just a simple linked list, so it's not hard for this program to follow it. So that's how it ends up getting pointed to the right system file, and we'll show you that in just a minute. Now, all of Flex file I/O is done as a byte stream. Just a byte at a time is what it typically sees. And so that's how this load routine works, is it goes and it gets a byte, this will be from the disk, and looks to see if it's a 2. A 2 means a data record. That's equivalent to those breakdowns we saw when we ran the map program. If it is, and it comes down here and it gets 2 more bytes, that's the address of where to put this section. Then it gets another 2 bytes, that's going to be the byte count, so it's a 16-bit counter, not just 8 bits. And then it loops going through and loading those bytes off of disk. Once it's done with that section, it comes back up here again and repeats it until it runs out of records or it hits this code of a 16, which is a transfer address instead of a 2. If you remember at the end of that system file, we had a transfer address of AD00. That's what would be caught with this 16. So then at that point, it gets that transfer address and then just jumps to it. And that's what ends up starting Flex. Now, the reason we had to write this routine is because at this point, Flex is obviously not loaded because this is loading it. So the disk drivers that we customize are not available yet. So this program has to know how to read the custom hardware. Like in this case, our serial I/O instead of an actual floppy disk controller. So that's what we do in these read sector routines down here. This is custom that we had to write to make it work with our solution for a floppy disk. Now, by the time I put in all of the routines to read and write through that, well, I don't have to do any writing, but read through that serial controller, this ends up bigger than 256 bytes. And I'd like this to remain under 256 bytes so it fits on one sector and so that I can use the routine to write this to the disk that comes with Flex. It only writes one sector. So what I've done is I've put the actual serial I/O routines in memory as part of the ROM process. So the ROM puts them in memory, uses them to read sector 0 here, and then just leaves them there. So you can see that here. This program loads at A100. The server I/O routines are at A300. They're just left there by the cold boot ROM, the ROM routine that actually loads this. All right, so that's the loader. But now, what is going to read this off a disk? We need something to read this off the disk and jump to it, so that it in turn can then read Flex off a disk and jump to it. And so we need a ROM to do that. Or in this Altair 680, it's kind of hard to burn a ROM. They're 1702s. Not everybody has that programmer. So I also wanted the ability to load a simple S record file and boot from RAM. So let's take a look at that one first, because that's the easiest way to do this until we get it all working. Then we can worry about the ROM. So this knows it's going to load that Flex bootloader at A100. This code itself is at A200, and then this one has the server I/O routines in it, and it's going to load them at 300 and leave them there. So the actual routine is pretty short. It clears the server, sends a read command, reads in a sector, and then jumps to it, and that's it. Here's the server read command, for example. And here's the server I/O routines that are at A300. You can see I org it right here at A300. And then these I just leave in memory. When we do this in ROM, we'll just have the ROM copy it from ROM down to this exact same spot. All right, so let's go to that machine and actually get this working. I've rebooted the machine just like we did previously, except now I've made our SearFlex disk 0, but I booted it by loading that all as S records like before. All right, so I want to get that Flex loader up here. I'll use the PC get xmodem routine like before. And let's see, flexload.asm. All right, so we'll assemble this here, and that'll give us a .bin file. So how do I get that .bin file out to the disk? Well, if you look over here, you can see there's a put loader command that comes with Flex. So what this does, it actually doesn't run at A100. What it wants you to do is put your loader in RAM at A100, and then put loader will take whatever's at A100 and write it to track 0, sector 0, or the first sector on track 0 for us. All right, let's go ahead and assemble this, flex load, and I'll suppress the listing in the symbol table file. So once we have this, we'll have a bin file. Then I'll load that bin file into memory, but not execute it. And we do that with the get command. Get is the other intrinsic command that is in Flex. Those are the only two, the mon command that I showed you earlier, and then the get command. So that'll put flex load binary up at A100. So let's do a get a flexload.bin. I'm not sure if you even need the bin. Okay, so now flex load is in memory at A100. Put loader will take what's at A100 and write it to drive 0. So is it correct disk in the drive? Yes, it is. All right, so now that has written that loader to the first sector on track 0. But it still does not have the starting address of SearFlex. Let's do a cat full of the SearFlex system, and you'll see it starts at sector 20 or track 20, sector 6. That's the information that needs to be written into that bootloader. Well, if you recall, the program link does just that for us. So I say link SearFlex. What that does, I was wondering if I had to put the sys. I guess it knew that part. What it does is it went to the directory, looked this up, and wrote it to offset 5 and 6 on track 0, the very first sector. So now that's in memory. So I now should be able to boot this. So let's go back to that loader. Let's go back to the monitor. Let me load that RAM boot that I created. Oh, I need to assemble it first. Let me go do that. I'm going to just do that here with the cross assembler, because all I need is the S record file. All right, now I have that S record file. Okay. So now let's send RAM boot S19. This is at A100 or A200. I made it where I can enter it either place. A100 is such a common entry, I just left it that way. This should load the first sector of track 0, jump to it, which should then load SearFlex.sys and jump to it, which should start Flex for us. Let's go ahead and, well, I can't get those both at the same time. We can see the activity. It looks like it's working. Well, there we go. And we are up and running. So that's it. We're basically done. We got this all working. You've seen me do demos of Flex. I'm not going to do a full demonstration of that. I'd have a good video that demonstrates Flex and relates it to how CPM works, which more of you are familiar with. I'll put a link to that. That's a good way to learn more about Flex. But now this is all up and running. You've seen me do multiple assemblies under this. There's cool commands on here where you can see how much free memory or how much free disk space you have. This is all done with a linked list kind of system, as opposed to like a block or a fat table like disk or not Windows, but DOS used in the earliest days. Windows still does, but it's much fancier. But this will actually go through and check all the free space left, You'll see this kind of jump around all over the disk because by the time you've done a bunch of things, your linked list of the free list has kind of gotten mixed up. It's not all just sequential sectors anymore. But anyway, so that does it for getting this booted with our little RAM boot routine. What I'd like to do next is a quick demo. I'll create the ROM boot version of this, actually burn a ROM, and then instead of using this PC for our disk drive servo, I'll just use a little Raspberry Pi. So at that point, I can just have a regular terminal. I have my Altair 680 with a little Raspberry Pi sitting next to it, completely standalone, ready to run with disk. So let's do that next. All right, now we've got a little Raspberry Pi sitting on top of here to use instead of a PC as our disk server. And we're just using normal CRT as our console instead of a computer. So you have the whole thing here just as if this was your disk drive system. You go ahead and turn on this computer, give it a reset. All right, at this point we have our dot prompt up over here on the terminal. All right, and jump to the ROM bootloader. I put that at FC100. And off it runs. So this is off doing a boot of the disk right now, and we're up already. And there's our prompt. We can see what's on drive 0. This was the drive we were working on before. Over on drive 1, I've got a basic disk. We can play with stuff on that. Let's go ahead and just run basic. It's on disk 1, so I proceed it with a 1. Basic is a large program, so it takes quite a while, pretty much like you've seen on CPM and other Flex machines. The responsiveness, the speed of this is about the same as using the 6800 and 5¼ inch single density drive. So it's not like you've lost anything, even though we're only running at 38.4 and we're running at a half-speed Altair 680. It does pretty well. Let's go ahead and load a game. Let's see if we can reload Lunar. Notice I'm having to type in the 1 to run off of that second disk. I can use the assign feature at the command prompt and make a work disk or a system disk to change that. I'll show you that in a minute. Anyway, so the program's in here now, and so we're up and running just like that. Put on some brakes, and perfect landing. Okay, we can go back to Flex if we wanted to do something else, but let's say you wanted to load a different program. Basic on CPM or Altair, you want to type files, or is it directory, or is it cat? None of those seem to work. One way is to go back to Flex and do a cat of drive 1 again. But now you're out of basic. Now in CPM at this point, you had no choice but to actually go back in and reload basic. But again, all these commands in Flex run in an area, not all, most run in an area up inside Flex. So this hasn't coppered basic at all. I can just jump right back to the warm start of basic, and we're in here just the same as we were. So now we could load chase.base if we wanted. Here's something interesting. I forgot the 1. You can put it there afterwards, and it still works. Pretty nice. Now these take a little while to load because it's loading it as ASCII text. It has to process each line into binary, tokenize it. Even on CPM, that takes a while when it's in source format instead of binary. All right, and now Chase is in there, and we could run that program too. All righty. Let's go back to Flex again. One thing that might be fun is to make this automatically continue with a command called continue and jump back into basic. So how did I accomplish that? Well, I actually wrote that little program. There's absolutely nothing to it. If you take a look at this, we got, let's see, what was it, continue.asm. This whole program basically, whoops, it's on drive 1. All it is, it starts at A100, jumps to 103, and warm starts basic. So that's a little program you could have written just to make it easy to get back into basic anytime you want, just by typing continue. All right. All right, well, that does it for this demo. This video's gotten kind of long, but this is Flex running very nicely on an Altair 680. It feels as responsive and quick as it does on the the Southwest 6800 with 5¼ inch drives. So not a bad solution at all when otherwise there have been no alternative to do anything besides paper tape on this machine. I'll put a link to information about the Linux version of the server. It's on the GitHub routine or GitHub page, and that way you can try that if you wanted. Or of course you can always run it on a PC with a terminal emulator as your console as well. Don't have to burn a ROM. We showed that. It's a great way to get more mileage out of your 680. Be sure to look at all the links in the description field again, and that should be everything you need in order to make this work.